welcome our viewers for this informative session on computational beyond the lab computational chemistry aspect. I work at the Department of Chemistry, Multimedia University of Kenya, and today we are going to dig deeper how this particular chemistry can assist in understanding of quite a number of things as we'll be looking at in a few in a while. Now, maybe we need to bring the aspect of chemistry, the way we understand it, and chemistry in general. It's one of the driving forces in our day-to-day lives. But as we do all that, we have to understand that computational chemistry tends to also assist in quite a number of things. So today we'll be unlocking some of these things for computational chemistry by just giving a few insights that maybe might assist the viewers in understanding one or two things about computational chemistry. So this will be my presentation outline, and so we look at the background about chemistry, a few examples that we can relate with, why computational chemistry, what role does it play in our current day-to-day lives, and where can it be applied? How does it complement other disciplines of chemistry and other fields of sciences? And when can it be applied?
That's quite, I think I am eagerly waiting to understand and also learn from you.
Okay, thank you so much. So that will be maybe by the end of this brief session, we'll have covered or addressed these 5 questions. If I was to do a bet, maybe I would have said you can place a bet. If we don't meet your expectations, then we are willing to maybe also honor that particular bet. Well, computational chemistry, of course, it applies it involves, you need to understand the principles behind computational chemistry. And if I need to understand those principles, then I must have a small background or understanding of chemistry. Now, when it comes to this, maybe understanding of computational chemistry, of course, in the field of chemistry, we are interested with chemicals that react to change, either physical or chemical change that could be happening in that particular field. So there might be physical changes, chemical changes, or even biological changes. But with computational chemistry, our main focus will be on the chemical and physical changes that might be happening. In any field of chemistry, that is the borderline of bond breakage, bond formation, as reactants and reactants come together, bonds will be broken and bonds are formed to as they form new compounds, new compounds. And therefore, the atoms are the ones that are responsible in these different changes. And some of the atoms, the bonds that are present could be broken, while others are going to be, new ones are going to be made or formed. And it's important to note that they, these atoms can neither be created or nor destroyed. So we are utilizing the law of conservation of mass, such that whatever you begin with must always end with a final product. For example, the simplest chemical compound is the water. Okay, it remains the same. We have two in this particular equation. We have two molecules of hydrogen, uh, which has four atoms. Then we have one oxygen molecule comprising of two atoms uh, combining to form two water molecules. Two water molecules. So this could be happening uh, in any scenario. Okay, so but I have decided to just use the oxygen, the water molecule as, so in this case, we refer to as elements as pure substances and cannot be broken down into a new one. But now the compounds that we are having on this right-hand side, we have now our compound, which is a combination of pure substances, combination of the pure substances. So the pure substances are on the left, the compound is on this other side of the right. And the equation is balanced, and the story can continue, and so on. So in all these chemical reaction story, uh, we have four atoms of hydrogen reacting with two atoms of oxygen. And when they react, where all those becomes our starting materials, they are what we are referring to as reactants. And whatever is yielded are two molecules of water, uh, which is our end results, or what we can refer to as the product. So there are different chemical reactions that can occur, such as decomposition. So you have a product breaking down into its independent constituents, like AB as our product. It breaks down into two products. We also have synthesis, which is the reverse of the decomposition. Okay, so you are beginning with the independent substances combining to form a compound. So this is an example of a synthesis process. We can also have a replacement. You are replacing single replacement where A, B plus C, the B is replaced with the C to form a new product called the AC and P. So you are just swapping the positions of this compound. You can also have double replacement, AB plus CD, to give us AB plus CB, and so on. So these are two compounds forming different, yeah. And all these make up a chemical reaction, and it can be equated in form of an equation. as you balance whatever is on the right and whatever is on the left. So this, you are correct, Dominic. This represent the synthesis process of water from its independent constituents. Okay, so there are quite a number of reactions that occur. For example, whatever is here, this is an oxidation reaction uh, where the metals combine with the rust process or the corrosion reaction, where you have a metal combining with an oxygen in presence of water, you have a chemical reaction. And that's why you find most of the vehicles that are in near the port or an ocean, their body parts tend to be sort of affected by the environment. So each and every day, several reactions could be taking place, whether we like it or not, they are taking place. And therefore, we cannot run away from the chemistry. So this represents a sort of a background about what happens in a lab setting. So what could happen? Are we able to bring this or mimic all this in or using a computer? And that forms the basis of computational chemistry. There have been a lot of information talking about computational chemistry is for the lazy chemist, but there's quite a lot of things that happens behind the scenes. And what if we only needed to press some keys on our computers in order to get the desired products? Our life could be very easy, and that could be very promising. For example, if you only want to know the bond type, you press letter B. If you want to know the bond distance, you press letter D. It makes our work easier, and so on. By just pressing any key on the keyboard, you have your results. But it appears as very easy from the way I'm explaining it. But so a lot has been happening in the field of computational chemistry, and we can integrate computational chemistry using the artificial intelligence. And so I want now to dig deeper on how we can bring in the AI into the computational chemistry. So a lot of digital transformation is taking place in our day-to-day lives. And if we look at most of these things in this flowchart, uh, we see if I want to dwell into material science, uh, I can be able to have digital materials design and have material informatics. Within the same, I can have machine learning in molecular designs of materials. And if I want to do simulation and modeling, I can do digital twins. We'll be looking at how that is later. We can also have quantum chemistry and several simulations. And nowadays, I don't require to always, if in Africa, because we have the disadvantage of not having all the resources for learning, we can have virtual labs that we can utilize to try and demonstrate some of the aspects of chemistry. We can also have the augmented reality. We have the virtual reality and the augmented reality. We'll be looking at it in a short while. So what happens in data analysis? A lot of data is generated in the lab, but are we able to make use of that data in making decision? And all these data, whether may it be big data and integrated data, how are we using it in such things like data-driven chemical reaction optimization processes, yeah, cheminformatics and data analysis, as well as chemometrics. Even in the field of chemical biology and digital medicine, a lot of AI-driven drug discovery work is being done, deep learning in structure activity relationships. We can also have structure property relationships that could be learned using by use of AI. Even in the supply chain, transparency and quality assurance. And this is where now we bring in the aspect of blockchain in chemical supply chain. How do we add value in all this? So what about the laboratory and the process innovations? We can use AI in spectroscopy and other analytical method development. At the same time, we can also use automated synthesis planning if you want to do uh, organic synthesis or you want to synthesize drugs and so on. How do we use AI in experimentation? We can increase our throughput in our day-to-day so that we optimize our processes. And how are we able to automate laboratory platforms, among others, even in environmental technologies, if we want to do predictive toxicology, and how can AI be used in environmental chemistry and sustainability? And all these can be complemented by use of what is called smart controls. We have a lot of Internet of Things happening, and how can it assist us in bringing closer this understanding of chemistry in our day-to-day lives? So this leads me to the first question of what is computational chemistry? In a layman's language, it is the application of mathematical models, algorithms, and computer simulations uh, to assist us in studying and predicting chemical properties and behaviors. So we can use computational chemistry, but we must have the understanding of mathematical models, basic use of computers, among other things. So why is it important? Because it's able to complement experimental chemistry by one, exploring molecular systems not easily studied experimentally. It can also assist the experimental chemist by providing atomic level insights. And very important, it's able to also assist in reducing time, resources, and other costs that are used in experimental chemistry. So what are some of the key goals of computational chemistry? So these may not be comprehensive, but some of the important goals of computational chemistry Number one is to predict molecular structures and properties, understand chemical reactivity, and some of the mechanisms that are difficult to comprehend. And we can also use computational chemistry in doing model interactions of large systems, especially if you're doing drug design, you want to do docking, and you're using bulk biological systems such as the proteins and other materials. This becomes one of the tools that is key in understanding that discipline. It also able to support the drug discovery and materials design. So in order for us to use computational chemistry, there are fundamental methods that one requires to have a good understanding of them. One is the computational quantum chemistry. This focuses on the electron behavior by using the Schrodinger equation. And some of the methods include the ab initio, which is a Latin word that means from first principles. And one of the best promising methods is the density functional theory, abbreviated as a DFT. Then we have the molecular dynamics. So this assists in studies of molecular motion over time. If, for example, I want to know the different infrared vibration modes, the molecular mechanics comes in handy in assisting us in doing most of these particular things. So it tends to simulate dynamic behavior under various conditions. Now, what are some of the tools and softwares that are applicable or that can be used in computational chemistry? So we have within the quantum chemistry, we have softwares like Gaussian, we have the GAMES, ORCA. Then molecular dynamics, we have GROMACS, AMBER, NAMB, among others. Then under visualization software, we have Primol, VMD, and Chimera. So, but apart from this, we also have integrated platforms like a whole software called Schrodinger, and we have another one called Material Studio, which uh, helps in the study of materials. But we also have Discovery Studio. It's a very good one for docking and use of other materials, drug design, and others. So this leads me to the question, where is computational chemistry applied? So I have narrowed to four, uh, starting with the basic research. So it can be used in investigating the reaction mechanism of different compounds and or understanding how is these reactions taking place. Then exploring exotic chemical systems that maybe have never been understood better. That can come very well. So in environmental chemistry, it can be used in modeling pollutant behavior and some of their degradation pathways. So as the pollutants are moving from one point to the other, what are some of the reaction or processes that could be taking place? And we monitor pollutants at point A, are those pollutants still present after some time, or as those pollutants are moving from one point to the other. So it can also be used in material science for designing maybe catalysts, polymers, and other advanced materials. Uh, and the list can be continue and continue. Then we have the virtual screening of potential drug candidates in the field of drug design and discovery. It can also be used in predicting the binding affinities with proteins, or what is called docking. Docking. So this field of chemistry has its advantages, and because technology is advancing, uh, all of us have, maybe technology is the one that is enabling us to be able to communicate. And sometimes this technology can have its own hitches. And as this happens, you it has its own advantages and disadvantages. Okay. And we can as well have a few examples or advantages. For example, when it comes to visualization, so this computational chemistry provides a detailed molecular insights of the atoms, of the atoms, the molecules, and others, so that you have a good understanding how this, you don't have to tell somebody how the molecules look like, but they can be able to see using their eyes. Then we have the accessibility advantage, because it enables exploration of some of the inaccessible systems, or things that we are limited in terms of resources. We may not be having the resources, and some of the equipments are quite expensive. For example, the XRD, it's highly expensive, but you can, if you know your crystal, how it looks like, you can actually get the XRD spectrum by just pressing a few buttons. Then the speed, it's also quick to simulate different scenarios at the same time. Then of course, the cost. It reduces the need for expensive reagents and equipments. Uh, in as much as it has its own advantages, there are a number of disadvantages, and therefore, one of them being the accuracy versus the computational cost. So if you want to improve on accuracy and precision, it comes at a very high computational cost in terms of the resources, the skills, and also storage capacity that you require to have. So it's a question of balancing precision with time and resources that you require to have. Scalability, this is the aspect of having to handle very large systems or long time scales, because some calculations can take long to process, but thank God we have some of the clusters that can be used, and they are available for use for different researchers. Then you require to have knowledge of both chemistry and the computational tools. So you need to have an understanding as an expert or as the user. So what are some of the future directions that we could be looking at when it comes to computational chemistry? How can we be able to integrate it with the AI, things like machine learning, so that we can be able to improve and enhance predictions and automate most of these processes. Uh, how are we able to combine quantum and classical approaches of the methods that are used in computational chemistry? And how do we leverage supercomputers and the cloud resources for enhancing high performance computing? Then how do we expand by maybe expand it or including it with the emerging fields such as the nanotechnology, uh, personalized medicine, and even renewable energy. And maybe I want to use, there's actually a chat GPT for, sorry, there's a chat GPT that I want to share in the chat. So we have this one. I had tried to do maybe the synthesis. The question was on how is aspirin synthesized, and it's able to give me the steps, the background about aspirin synthesis, the reaction equation, reaction mechanism, how is it purified, and all this information. So we are not left out as people in chemistry. You don't require to use the chat GPT only. And we have this other one for, so I have only used one AI-based technology in chemistry, but there are quite a number of technologies that we can leverage in. So I have shared another link. So of course, it's going to take you to this article that was published recently, actually this month. And it has a lot of information on AI-based technologies that we can borrow from. And one can read further on all that. And as I wind up, there are these AI tools for chemistry that these two, but there are quite a number that so we have applications in uh, metabolomics in the first image here. Things to look at how does some of the reactions takes place for in a biological setup. And we can also use Internet of Things to like this, so that we have control systems that can assist in either drug design, and how can we leverage the big data by doing several biological pathways and some of the levels of optimization, and where can we do that. And then I talked about virtual reality versus the augmented reality. So this is an image of the real workstation where we have the mixed reality handset. Here it is. We have the motion capture sensors, and these can be mixed with some reality view in a human kind of setup. Uh, okay, so in conclusion, so some of the key things maybe that we have looked at. Computational chemistry is a powerful complement to experimental methods. It also drives innovative, diverse fields like drug discovery, the material science, nanotechnology, nanoscience, and so on. There are also future advancements. How will they further expand its scope and the impact that we have? So maybe the big question should be, are we able to embrace computational chemistry in our day-to-day activities by asking deeper questions so that we are able to uncover new chemical insights? So we have one tool called ChemDraw. Is one of the tools that, so I'm using one of the, it may not be the latest version, but I want to convert a name to structure. And I just want to work with the example that I had talked about, aspirin. So this is the structure of the aspirin. I can, if I know the name, I can convert it to structure. And so this is what I want to demonstrate today. After you have obtained the structure, you can go ahead and do either retrosynthesis. So they have introduced different fragmentation tools. So I can break it down. If I want to know, if I cut on this side, which, so I have my, what do you call it? I have my aspirin on this side, and I have the two reactants that I can use to form these products. Okay, so that's one. If I can go further, and if I want to, so this is where I have the reactants on the right, but I can, you remember we talked about different types of reactions. Okay, so you can have the reactants on the right, or decomposition. So I can have this, if I have this and I want to break it at this particular point. So I have this aspirin can be broken down to give us these two fragments. I hope we are still together. So I can copy this and I bring it here. And so lastly, I can try to break it down even at the middle. So it gives me the chemical formula, the exact mass, and the fragments. So I have one fragment on the top left corner and this other one. So we have two fragments. So I can quickly get the fragments of these compounds and so on. So that's where we are in terms of ChemDraw, Chem 3D. So I want to open the 3D one so that that was 2D, the 2D. So let me share the 3D one. So the 3D integrates, we have on the right, we have the ChemDraw 2D. So I can convert name to structure. I can still work with aspirin, or maybe I talk of methyl paraben. So this is this, And I can do, if I want to rotate it, so it's rotating, what is called, I can rock it, I can do spinning, uh, among others. So there are quite a number of things that can happen, or understanding of the molecule uh, in the 3D. 3D. So it's integrating both 2D and 3D. And yeah. So maybe with that, I want to stop there and see whether there is any question, any clarification.
Hello. Uh, okay, thank you for the wonderful uh, the webinar. I have learned a lot on how like computational chemistry could be applied in so many aspects. Personally, I'm interested in environmental monitoring, and my question is on is there a model or is there a way that we could do maybe real-time computation using IoT? And sorry, I missed the introductory part. So, is there any prospects of collaboration, or are you like providing any tools or platforms for implementation of such projects, or is there like a provision for future engagement? Thank you.
Okay, thank you. Thank you. This is Dominic. Yes, Dominic, for that question. So there exist quite a number of tools, and actually you have, I think, maybe touched at the heart of some of the things that I do on computational or geochemical modeling. So geochemical modeling is where now you want to see things like if I have the water, the soil, or maybe the solid and also the gases. How are they interacting as they form new compounds? And if you have pollutants, how are they affected as they move from one point to the other? And there are quite a number of tools. Maybe I'll list a few. So one of them being geochemical workbench, geochemical workbench. But we also have Frixie, Frixie. So Frixie is an acronym for pH, redox, equilibria, and C is the programming language that is used in running that particular program. And maybe just to show you some of the work that we did, like maybe real time. So this is the assimilation of some of the work that we have done before, or to monitor some pollutants with effect of time, like 50 years. So, and if we were to do it for 50 years, then maybe some of us may not be live to do most of this or to see the end results. But with just these computational tools, we are able to mimic what happens after the 50 years by just doing some calculation on that. We actually have an application that we developed for monitoring when you are in the field. It's able, if you have the physical chemical data, then one can see it is going to generate for you the simulations. The simulations, if you have the physical and chemical parameters. Yeah, so So there is quite a lot that can be done on this field. I hope I have answered your question, Dominic.
Yeah, is it possible to get access to the slides that you've shared about your application? I'm really interested in that application, and like I was asking about the prospects. So, is there provision for collaboration, or are you empowering us to like create our own tools like that? And also, is it when I was asking about real time, is it something that we can deploy, let's say on the cloud, and then like we run it every time we have new data from the sensors, or is it something that is you have to run it offline, like you have the initial data and then you feed to the program? Thank you.
Yes, you can. It works both ways. If you are in the field and you are able to monitor some parameters in the field, because what happens in computational chemistry, you have to have, we call it garbage in, garbage out. So if you feed it with information, depending on the command that you give it, it's going to generate for you quite a number of data. Of course, we can collaborate, and I'm also willing to be available to train and assist anybody who may be interested in this particular field. Of course, this information, if I don't share it, it's not assisting me. So I will share my email and my mobile number. You can always reach out for maybe further information on the same.
Thank you so much. I'll reach out as soon as possible. So I have a few areas that we might work together on modeling on the environmental systems, ecosystems. Thank you.
You're welcome.